Okay, today we are going to be talking about kinetic molecular theory. Oh, no. So the idea is that if I have a vessel, I'll just have to deal with my left-handedness here, in 3 dimensions, X, Y, and Z. I know you're not used to it in those particular terms, but I've got this dimensions, and I want to determine the interaction between the gas on the inside of this vessel and the outer walls. So what I have to do is actually take a look at what's going on here. So when I have a particle, it's moving around, it will exert a force on the wall and it will bounce back. It's a collision. It's going to be a perfectly elastic collision. Might not be, but in our case it is. We are talking about the ideal case because that's what we do to start with. And so that's going to be a collision. And then it's going to exert that force. So since it's a collision, whenever we hear the word collision, the first thing you should think of is, oh, momentum is conserved in a collision if I've identified my system. Well, we have definitely identified the system. And so we are going to say that the change of momentum of that gas particle is the mass of the gas particle times its change of velocity. And we're only going to be looking at that one direction for now. Okay. And so I can easily deal with this. This isn't too bad. Well, this change of momentum, mass times change of velocity, what I really want is pressure. I'm going to be looking at the force. So the force is the change of momentum divided by the change of time. That's your impulse momentum theorem. Remember, J, force times change of time is change of momentum from back in physics 1. And so this is just a fancy way of writing F equals ma. And so we have m delta v in the x direction, I'm only talking about one dimension here right this second, divided by time. Well, the problem is I don't have any time. I don't know what that time looks like. And that delta v, that's kind of a problem here. So let's take a look and get, because delta v divided by delta t is a. So there's your F equals ma. So let's look at my delta v. Well, coming back to that picture, I started out in this direction. I'm going out, and so that's my v initial x direction. This is my v final x direction, and so delta v is v final x minus, and notice they're in opposite directions. So minus a negative is a positive, and so delta v in the x direction is just v x. Oh, sorry. Misspoke there. That's got to have a 2 in there. So that's a 2. And we remember that from back in physics 1. So we're going to make that a 2m vx, not delta v now, just the measure of the speed. Well, this time, that's going to be the time between collisions. So we know that delta v, or v, not delta v, sorry, my fault there. V is defined to be the change of position divided by the change of time. Well, so that's just a velocity, and that's why it's important it's not the change of velocity. So this speed is how long it takes it between collisions. Well, the time between collisions is actually twice the x. So I'm going to then do this. So delta t is 2 delta x divided by v. because it's got to go all the way over and all the way back. It's got to have two of those. And that's going to give me my delta T. Okay. And you don't need to write the delta there. You can just write the x. So that's going to be 2x over v of x. And so then my force, my 2's cancel. Isn't that lovely? And I've got mvx squared over x. As the denominator of a denominator is a numerator. And that's x, that's velocity squared. Well, this is now beginning to look really interesting, isn't it? Because mv squared, anytime anybody says mv squared, your brain should immediately go to kinetic energy. And by gosh, yes, it will. Okay. Which is also kind of cool if you're looking at it and thinking about it. Well, that's just saying that force times distance equals change of kinetic energy. There's your work energy theorem. We've done the, yeah, we have run the gamut, have we not? Okay, so now I've got an issue here. This isn't a real problem. I can measure this. But the real problem is that measuring that force due to this particle, and that's just in this x direction. Well, the thing is, if I'm talking about the x direction, that's going to be probability wise the same. I was looking for a better word. I didn't have one. Same as the z direction. And so Vx squared is roughly 1/3 of the total average velocity squared. Because I don't just have particles moving in the x direction. I have them moving in the y direction. I have them moving in the z direction. And so, but that's just my x. Well, this is the force just on the x wall. I want all the force. I want it all. So this force, and that's what's going to happen here. What I do know is I can't measure the force real easily, but I can measure pressure. And I know that pressure is force divided by area. Force divided by area. Okay. And I know that area is defined to be the volume divided, okay, crikey, I said this incorrectly, my fault. The volume is defined to be the area times the height. They always say, oh, the volume's length times square times width. No, the volume is the area times the height. So when you're talking about a cone, that's where your 1/3 comes because it's the area and you've got a dr dt issue happening there. Or sorry, a dr dh issue happening there. And so but in general, that's where your cylinders come from. So I need this to work not just on a rectangular prism, but I need it to work on a cone. I need it to work on a sphere. I need it to work no matter what the shape of my vessel is. So this H, I'm just going to say, is X. And so A is the volume divided by X. And so my pressure is the force divided by volume times X. And this is mighty interesting. We're going to put a little asterisk around this. Actually, I'm going to put a highlight here because we're going to come back to that bad boy. That's going to be important in just a few minutes. And so what I have here is my pressure is force. Well, I have my force. Well, that's 1/3. So my force is 1/3 m total v squared, because I need all of the particles that are moving, divided by x, there's my force, times x, divided by volume, and that equals the pressure. Well, let's do some fun stuff here. The x's cancel. Isn't that lovely? And so I am saying that the pressure is 1/3 times mv squared over the volume, which now means that my pressure times volume is 1/3 mv squared. And I left something out here. Yep, nope, I sure didn't. That's perfect. That's perfect. Well, this right here is 2 times the kinetic energy, because kinetic energy is 1/2 mv squared. So pressure times volume is 2/3 times the kinetic energy. And that's the average kinetic energy of the particle. Can I measure the volume of a vessel? Why, yes, I can. I most certainly can. Can I measure the pressure? Yep, actually, it's pretty easy to measure pressure. We've got pressure gauges, we have barometers, we can do that relatively easily. The problem here, pressure times volume is equal to energy. Remember up here I've said, hey, we're going to come back to this. Pressure times volume is force times distance. This is work. Pressure times volume is work, is energy. Pressure times volume is work, is energy. Don't believe me? Let's look at the units. Pressure times volume. Pressure is force. I'm sorry. Shoot, gosh darn it. Force per area. That's newtons per meter squared. Meter squared. Volume is cubic meters. Bam, bam. That's a Newton meter, and that's a joule. Pressure times volume is energy. Now, all you chemistry people, you are thinking to yourselves, but wait a minute. Pressure times volume, PV equals nRT, because the chemists tell us PV equals nRT. Now, chemists did this by experiment. We proved this. We didn't just say, huh, that sounds good. No, they actually Boyle and Charles and Gay-Lussac and Kelvin, and they worked on this. They discovered this relationship purely by experiment. Well, the physicist, mostly Kelvin, he's coming along and he's doing all this stuff. And this is why temperature always has to be in Kelvin, because temperature, let's take a look. A equals B, A equals C, therefore B equals C, and nRT is 2/3 times the kinetic energy. That means that temperature is the average kinetic energy of the system. Temperature is energy. That's why you must use Kelvin when you're doing your calculations. Your chemistry teacher, I am sure, told you this. He probably didn't go into this gory detail. And so now we have to take a look at what this means. N is the number of moles. Number of moles. R is the ideal gas constant. And then T is temperature. So if I were to do this, I would say that the average kinetic energy of a system is 3/2 nRT. Well, N is the number of moles, and if I take N is the number of particles divided by Avogadro's number, then I can also write a relationship, and this is just another fancy way of saying it. nR is equal to the number of particles times K, and this is Boltzmann's constant. And they're just numbers. Those are constants. Whether or not you're using the number of particles and K and the number of moles and R depends on the situation that you have. but the kinetic energy is equal to the 3/2 nr or 3/2 capital N kT, if you're dealing with the number of particles, which means that if I'm changing the kinetic energy, I'm changing the temperature. If you're changing the kinetic energy, you're changing the temperature. And that's a big deal. So we can say 1/2 mv squared, and that's your root mean square that we just talked about, is 3/2 nRT. And so you can now find a relationship between temperature, velocity, kinetic energy. In our next lesson, we're going to talk about pressure and volume and the ideal gas constant and a lot of that. And the very next lesson, it's not a lesson, we're going to work a couple of problems that deal with this and working with the ideal gas law. Just bear with me, and hopefully we're all in this together.